All right, let's finish section 8.3, inverse trigonometric functions. Okay, so let's do a few examples now where we mix inverse trig functions with other trig functions that are not the inverse, they're not related to each other. So we can also evaluate compositions where the trigonometric function and inverse trigonometric function are not inverses of each other. So like sine of cosine inverse. Okay, and so expressions of the form like the inverse function on the outside can usually be evaluated by direct evaluation from the inside out, okay, when x is a special angle. Okay, and that's pretty common that those types you can just evaluate from the inside out. Expressions of the form where the inverse is on the inside can sometimes be evaluated from the inside out if there's special angles involved, but this situation is often presented with non-special angles or even variable expressions on the inside. And if that happens, then we have to get a little bit more creative, maybe using some of the Pythagorean identities or drawing a picture of a triangle. Okay, so let's do these last few examples and we will call it a day. So evaluate each of these following, and so for these, I'm noticing that we've got the first few here have the inverse part on the outside, and the inside parts look like they might be nice special angles, so let's just do direct evaluation from the inside out. So for this one, I would just write it down as sine inverse of, okay, and then we just got to do cosine of 2 pi over 3. All right, so cosine of 2 pi over 3, got to think about that on the unit circle. That's the second quadrant with a pi over 3 reference angle. So cosine comes out 1/2, and in the second quadrant, cosine is positive. That's actually incorrect, right? Cosine is negative in the second quadrant. I just had to think about that. Right? Doesn't hurt to write that down to remind yourself. So yeah, cosine is negative in the second quadrant. Okay, now we do sine inverse of negative 1/2. And so this is where you have to use the domain restriction. So this is where you think to yourself, what angle causes sine to come out negative 1/2 in the interval from negative pi over 2 to positive pi over 2? So sine comes out negative 1/2, it's going to be negative, and it's the pi over 6 angle. All right. Moving along, this looks like it could be a special angle, so we're going to just do cosine inverse on the outside and we'll evaluate that. However, 15 pi over 4, I think that's more than one time around on the unit circle, so we might want to do a little bit of work in there. Let's do some scratch work. 15 pi over 4, let's subtract 2 pi to find out the reference angle that's only in the first time around. So that's going to be minus 8 pi over 4. And so what do we get? 15 pi minus 8 pi. This tells us, this tells us that we are going to be at 7 pi over 4. Okay, so we need tangent of 7 pi over 4. Okay, so tangent of 7 pi over 4. Pi over 4, we know that it's going to be a 1. And 7 pi over 4 is in the fourth quadrant, and so tangent is negative in there. Okay, yeah, don't forget all these old techniques. You could have angles that are beyond 360 degrees, and so you got to work out what is the reference angle, what is the coterminal angle from one time around. Okay, and now we can go cosine inverse of negative 1. Remember that cosine inverse has to go from 0 to pi. And so we choose, where does cosine come out negative 1 on the interval from 0 to pi, and it comes out at pi. And stuff that also helps me think about that is the cosine graph looks something like this, and I know that at the pi location, that's where it reaches the negative 1. So all kinds of stuff. I mean, there's so many different little techniques that we're building throughout this semester to start memorizing these things. Okay, tangent inverse of sine of 5 pi over 6. So that's a special angle, so we can do direct evaluation from the inside out. So sine of 5 pi over 6, so pi over 6, I know that sine is 1/2, and 5 pi over 6 is the second quadrant, sine is positive in the second quadrant. So where does tangent come out 1/2? Well, let's see, does tangent come out 1/2? It does, but that's not a special angle. So for this one, sine of 5 pi over 6, and we need tan inverse of this 1/2 number. I think I gotta just grab my calculator now, and I'll go mode, I'll switch it over to radians, and I'll go second tangent inverse of 1/2, and we get approximately 0.4636. All right. So yeah, that did not come out as a perfect value for the tangent. All right, example 9, let's evaluate sine of cosine inverse. So this time the inverse is on the inside. So there's a couple of different ways of doing this. And I want to really emphasize this one actually is not too bad because I'm noticing that the inside is a perfect number that comes from the unit circle. Okay, so we can actually just go directly sine of, and then let's work out cosine inverse of √3/2. So what angle causes cosine to come out positive √3/2? In the interval from 0 to pi, obeying the cosine inverse domain restriction. First quadrant, that's just going to be pi over 6. Okay, and then we can evaluate sine of pi over 6, and that is 1/2. Okay, so not too bad as long as you recognize that that did in fact have a nice angle involved, right? One of our special angles was involved. Okay, but on the last page here, I've got a couple that do not have special angles involved. So here we go, tangent of cosine inverse. So 1/3 is 1/3 on the unit circle as a special angle, and that's a no. Okay, so there are a couple of different ways that we can do this. I'm going to show you the technique that I like the best, and it really is drawing a picture. Okay, so note that cosine inverse, this is just going to come out, this is just going to come out as some angle. That's just going to be some angle, and then what we need to do is find the tangent of that angle. So we can actually find this answer without ever knowing what that angle is. And so this is the technique that I like to use. Cosine inverse of 1/3. Okay, so this is going to be in the first quadrant. And so let's get a picture going here and say, all right, here's the angle. And then how does cosine work? Cosine of an angle is adjacent over hypotenuse. So if we look at this, the only way that this angle that I'm starting to draw here can make sense is the 1, that's got to be the adjacent, and the 3, that's got to be the hypotenuse. Now it doesn't necessarily have to be exactly 1 and 3, it could be any multiples of those. It could be 2 and 6, or like 10 and 30. But the point is, when we do the trig functions, it's always going to reduce down to 1/3. Okay, and so the reason why I do this drawing now is in order to evaluate tangent of this theta, we need to find out the opposite, right? Because tangent is opposite over adjacent. So since tangent of this same angle that we're drawing here is the opposite over the adjacent, we just need to actually work out the Pythagorean theorem. So I don't know what you want to call this. Maybe let's call it y because it's like the y direction. And we can work out the Pythagorean theorem to find out that value. So here we go. We can go like 1 squared plus y squared equals 3 squared. Okay, and so this is 1 plus y squared equals 9. And subtract 1 everywhere, we get y squared equals 8. And taking the square root of both sides, we get y equals plus or minus, and the 8, you can break that down. That's not a perfect square, but remember that you can break it down as a 2 can come out with a leftover, so 2√2. Okay, and I specifically put plus or minus on it because it makes a huge difference. Whenever you're solving by taking square roots, you do have plus or minus, but then it's also really important to notice which quadrant we're in. So pretty much obviously in quadrant 1, the y value there is positive, so we're going to pick the positive version. So this is going to be 2 root 2. Okay, and so notice that I'm kind of doing like a little loophole. I'm bypassing. I don't even need to know what that theta is, because now we can actually just evaluate tangent of theta. And tangent of theta is just going to be 2 root 2 over 1. Opposite over adjacent. So that's 2 root 2. All right, cool stuff. So I never even knew what the angle theta was, but if you draw a picture and you just relate this angle on the trig functions, how they work with the adjacent, the hypotenuse, the opposite, all of that kind of stuff, then you can work it out and find out the answer. All right, so cool stuff. That's the way that I would recommend doing these. Same with number 11 here. We're going to draw a picture because this is definitely not on the unit circle. This x over 3, I mean, this is what I'm talking about. Sometimes there's variable expressions involved. So for x over 3 here, I would just recommend doing the picture. And so here's theta. So I don't know, remember that sine inverse of a fraction comes out an angle. And so if we get a picture going here, and so for the x over 3, they did tell us this restriction where x is in between -3 and 3. So let's go ahead and just get an angle going here. Let's get an angle theta going here. Remember that sine, so I'm trying to think about how I need to label stuff. Remember that sine of an angle is opposite over hypotenuse. So if I'm looking at sine of this angle theta here, it has to obey the x over 3 is the opposite over hypotenuse. Now that's a little awkward that that's called x, because I usually like to call the vertical direction y, but if we've just got variables involved, then that's just got to be x. Okay, we want to come up with a simplified expression for this in terms of x. So I got to get, for cosine, we need the adjacent, right? So for cosine of the angle, we need the adjacent over the hypotenuse. Okay, so we need to find out what this side is right here, and there's just going to be an x involved. There's no way around it. Okay, so I need to call this a different variable. I don't know, how about, let's just call it, I don't know, how about a? I don't want to call it y. Let's call that a. And so now we can actually find out what a is in terms of x by using the Pythagorean theorem. So we know that it would be a squared plus x squared equals 3 squared. Okay, we're pretty much doing the same thing that we would have done if we knew what all of the numbers were, like in the previous example. Okay, so now I want to solve for a. So let's, we have a squared plus x squared equals 9. And if we were going to solve for a, you just subtract this from both sides. And we have a squared equals, and you can't combine those. And then we take the square root of both sides, make sure it's the entire side. And we get a equals plus or minus the square root. And don't touch each of those because you've got subtraction in between. You cannot do the square root of each of those pieces separately if there's subtraction involved. Okay, so this a, remember when you're taking the square root of both sides, it does have to be plus or minus. Okay, now the way that I drew this, I drew it in quadrant 1, and I'm not actually specifically sure if this is in quadrant 1. So I need to go back up to this expression here. They said -3 is less than or equal to x, which is less than or equal to 3. And I think all that means is look at this expression that we have here at the end. This expression, if there's like a domain restriction because you can't have square roots of negatives. So I think that's all that matters. So that piece right there really doesn't make a whole lot of difference, except that we can't plug in values of x that are like bigger or smaller than -3 and +3. I think that's all that that means. Okay, so I think it makes not too much difference if we just go cosine of sine inverse of this x over 3. We can just write it as, and I'm pretty sure that we can just pick the positive version and it won't make too much difference because x is going to be involved anyways. So we know that cosine of an angle is just going to be the opposite, no, cosine adjacent over hypotenuse. So we found out that the adjacent is 9 minus x squared over the hypotenuse is 3. Okay, and I'm just choosing the positive version there because there wasn't any extra information about what quadrant we needed to be in or anything like that. Okay, there's a chance that you might need to put the plus or minus version in there just to say that there are two different possibilities depending on the quadrant that you're in. But for sine inverse, yeah, we don't know if this expression is positive or negative, so there could be the two different possible answers. So I think just to be on the safe side, unless I got any extra information, I would go ahead and put the plus or minus there. Okay, so yeah, we're drawing a picture. If it's some variable expression in there, or if it's some kind of a fraction that's not on the unit circle, draw a picture and you can bypass the whole process of not ever needing to know what the theta number was. All right, so yeah, that's going to be my recommendation for how to solve these ones, is drawing a picture and labeling the triangle based on how the trig function is defined. All right, so that finishes off section 8.3. Hope you have a good day.